Okay, so we're going to start now with chapter 7, which deals with the atomic structure. And in chapter 7, we're going to meet some things that you would have learned earlier in your high school or introductory chemistry, but we're going to delve into it in a more detailed fashion. And let me just warn you, and this is true for chapter 7 and for chapter 8, that the topics that are being dealt with here are rather abstract, even though they're very important in terms of our understanding of how atoms behave. So it might take you some, it might be difficult for you to appreciate the first time. I remember when I was a student, I struggled with these topics, atomic structure and um, and the electronic structure of atoms, which we're going to deal with in chapter 8. Okay, so with that said, let's proceed. So a little bit of history here concerning how we arrive at our current understanding of the atomic structure before electrons and other small particles, protons, etc., behave the same way as normal sized objects. In other words, back then it was believed that these particles obey the Newtonian laws. Then experiments were done with light in an effort to understand or confirm the fact that particles do behave this way, and it turns out that that is not actually so. So that has led to our current understanding of the behavior of electrons in atoms, which is described by the quantum theory, which we're going to get into later on. Okay, so that's just a very brief history. We're going to get into it in more detail in this chapter. So let's talk about the discovery of this particular phenomenon known as cathode rays. It was discovered by Johann Hittorf in 1869. And basically, these rays are formed in this setup that you see here. So this is a schematic representation of the experiment that was done by Hittorf. Basically, this consists of a tube which is evacuated. So this part here is connected to a vacuum pump which pulls all the air out of it. And then you have two electrodes here. You have the cathode and you have the anode, which is connected to an electricity source. So this could be a series of batteries or a series of cells which make up a battery. And basically, once circuit is completed, what one will notice is that you're going to end up with a stream, basically a beam emanating from the cathode and moving towards the anode. Now you'll notice that the cathode is negatively charged and the anode is positively charged, and that's because they're connected to the positive charge here, or the positive part of the cell collection right here. That's the anode, and the cathode is connected to the negative end, right? So that's why we know what the charges are for the different electrodes. So by virtue of the fact that the stream emanates from the cathode to the anode seems to indicate or imply that whatever makes up this beam of particles, the particles themselves are negatively charged, all right? Another property of this stream is that they always travel in a straight line. However, if you put next to it or close to it an electric field or a magnetic field, then that beam will be deflected. And that is demonstrated in this picture here, which basically replicates what I showed you earlier. This is the beam right here, and you'll notice that it is attracted towards the magnet, which is placed down here, all right? Another property of this beam, known as cathode rays, is that they cause glass and other materials to fluoresce. In other words, when they hit glass, the glass lights up, all right? So those are just some properties that were displayed by this newly discovered cathode rays. Okay, so once this was discovered, like any new discovery, a lot of scientists start investigating and trying to understand, the nature of the new discovery. And J.J. Thomson, an English physicist, he did some work because he wanted to find out the exact nature of these particles. So He made some modifications to the original experiment, and what you see here is the result of that. Let me just describe what is happening here. So basically, we have our evacuated tube, but you have several compartments to it. You have the cathode here, which is connected to your electricity source, and the anode, which is connected to, again, to the same source, is this right here. All right. Actually, it is right here, the anode. But the difference is between this setup and the previous one we saw for the anode is that this anode has a slit in it. All right. So that slit allows for the cathode rays, which originates from the cathode, to be attracted to the anode, but they have enough energy to pass through the slit. And there's another slit here just to ensure that we end up with a beam, right? A narrow beam. Now that beam is allowed to pass through this region. And you'll notice that in this region here, you have two magnet poles right here, north and south poles. And you also have two plates right here, which basically produces an electric field right here. And we know that because these plates are connected to another battery source right here. All right. And then you have at the end of this part of the apparatus, you have a scale here, which basically measures the angle of deflection of the beam. Now, that happens, the deflection of the beam happens because of adjustments made to the magnetic field and the electric field, right? So you can basically vary the magnitude of the electric field, let's say, and see how it affects the deflection, the angle of deflection, right? And the same is true for the magnetic field, all right? So that's basically the setup for J.J. Thomson's experiment. And based on, this setup and calculations done, he came up with the ratio of the mass of the electrons to the charge. And he discovered that the mass of the electrons, which make up the cathode rays, to the charge is equal to minus 5.686 times 10 to the minus 12 kilograms per coulombs. Let me just say here, and I probably should have mentioned this before, that the electrons were discovered to be what makes up the cathode rays, right? And later on, people came up with the term electrons to describe these particles, right? So he discovered that the mass to charge ratio of these particles known as electrons is equal to minus 5.686 times 10 to the minus 12 coulombs, all right? Actually, kilograms per coulomb. Okay, so, of course, scientists are not satisfied enough because while this is very important, the mass to charge ratio of these particles, we want to know exactly what the mass is and what the charge is. So another scientist came up with this experiment. Now, mentioned here is the person who is credited with the term electron, right? Stoney is the person who came up with that term. Now, this guy, Millikan, a Dutch physicist, he designed this famous oil drop experiment, which is shown here. I won't go into all the nitty-gritty details involved in terms of how this determines the charge of the electron, but basically, as you can see here, it consists of two plates, metal plates, which are connected to an electricity source. This is the cathode, this is the anode, and we have some oil here in this bottle right here. And as you can see in the setup, it allows for a fine spray of oil to be ejected from the nozzle right here. One thing I should say here is that there's a very tiny hole in the cathode plate, which allows for individual droplets to pass through. And once it's passing through here, the oil droplets are subjected to ionizing radiation. And what this does basically is knocks off electrons off the oil drop, and therefore, as a result, the oil drop is positively charged. Now, because we have an electric field here generated by these two electrodes right here, the oil drop can be made to be suspended between the two, right? So based on the fact that you can suspend the oil drop, which is positively charged, between the two, and you, of course, would have some other data information like the size of the electric field and the current that is flowing through the external circuit, one can calculate, and he actually did calculate, the charge on the electron. And he discovered that the charge on the electron is minus 1.602 times 10 to the minus 19 coulombs. All right. So we have two things discovered so far up to this point in time. We have the mass to charge ratio and we have the charge. So if we know those two, all we have to do is multiply the mass to charge ratio by the charge of the electron, and we end up with the mass of the electron being equal to 9.109 times 10 to the minus 31 kilograms, per electron. So that's basically the history behind how we now know what the mass of the electron is and what the charge on the electron is. So now that we have discovered that atoms have electrons, the next question that arose, which were investigated by the scientists of that time, was, okay, how are these electrons, how are these particles arranged in the atom? So J.J. Thomson, who we saw earlier, came up with the apparatus for determining the mass to charge ratio of the electrons. He came up with his version of the atomic model. So he proposed a model where you have the positively charged sphere, which would be which would contain what we now know as the protons, with individual electrons spaced between themselves within that large positively charged sphere. So he proposed, for example, that in the case of the hydrogen atom, there's only one electron that is present right in the center of that sphere. And in the case of a helium atom, the two electrons would be spaced equally along a straight line through the center, again in that sphere. Now, this model is known in some textbooks as the plum pudding model, all right? So this is a picture of what he was talking about here. So he was suggesting that in the case of the helium atom, this is how the particles would be arranged in the atom. These would be the electrons, and then we have the positively charged nucleus right here. And if this were to lose one electron, then the remaining electron will simply go right to the center. So that's basically the model that was put forward by J.J. Thomson. Of course, that is just a model. It's a theory. Well, actually, to be perfectly accurate, it was a hypothesis, because my understanding is that no experiments have confirmed this. So that is the reason why this guy, Rutherford, an English guy, he came up with an experiment to test this particular hypothesis. And the way he did that is that he took a metal foil. If I remember correctly, that metal was made up of gold. And he had a source of alpha particles, which is radium. Radium is very radioactive and will spontaneously emit alpha particles. Now, if you don't know what alpha particles are basically the nuclei of the helium atom, and they are positively charged, right? So basically, the alpha particles, which are positively charged, will be shot from this area right here, where the radium is producing it, straight directly to the metal foil here. Now, here's the idea behind this particular model. What this model is looking at is testing J.J. Thomson's hypothesis. What J.J. Thomson is saying is that the bulk of the mass of the atom, or the bulk of the space occupied by the atom, would be the nucleus. If that is true, then when these particles, which are positively charged, hit the atoms that make up the metal foil, they simply should be repelled in the other direction, because basically you're going to have a positively charged particle coming into contact with a relatively large positively charged particle. So that's the expectation. But what he found, as you can see from this diagram right here, is that in fact, most of the particles will pass right through the foil and will be detected on the other side. Now, some of them will be deflected, as shown by this line right here and this line right here. In fact, some of them will even be turned back in the opposite direction, as shown by this line right here. But the vast majority of particles will basically pass right through the gold foil, right? So the conclusion is that the actual positive charge of the atom is not constituting the bulk of the volume of the atom. The positive charge basically is very, very small, so small that the stream of particles can avoid it, as shown in this model right here. So basically what Rutherford is saying, based on his data, is that when these particles, when the alpha particles are shot at the metal foil, most of them will not even come close to where the nucleus is, which means that the nucleus must be a very small concentrated region in the atom. So as you can see by these red lines here, labeled 1 in each case, these particles will just simply pass through the atom without even coming close to the nucleus. Now you may have a couple of them which comes within close proximity of the nucleus, such as the pathway numbered 3 will come relatively close and be deflected at an angle, as shown here. And then you have others which will, by chance, come into direct contact with the nucleus and then be turned back, as described by the pathway here labeled 4. But most of them will pass right through the atom without coming close to the nucleus. So this contradicts the J.J. Thomson model, which says that the nucleus takes up most of the space of the atom. It turns out that the nucleus, based on Rutherford's experiment, occupies a relatively small space of the atom compared to the size of the atom itself. Okay, some other things I want to talk about, some other particles that were discovered. Well, based on this experiment, Rutherford was able to determine the amount of positive charge that is present within the particular atom. And of course, I won't go into all the details about how that was discovered. Suffice to say, these positive charges were carried by particles which were called protons. And this introduced the concept of the atomic number, because it was discovered that respective elements have their own unique number of protons in the nucleus of the atoms. So that's what basically the atomic number was defined as, which is the number of protons in the nucleus of an atom. And then relatively later on, another English scientist by the name of James Chadwick, he discovered the neutrons. Again, I won't go into the details about that, but basically he discovered that the neutrons have approximately the same mass of protons, but no charge whatsoever. Okay, so those are the particles that basically make up any atom of any particular element. Okay, so let's talk about mass spectrometry. This is a very important technique, especially for those of you who plan to do organic chemistry. You'll be using this to some degree when it comes to the structure elucidation of organic molecules. But what I'm going to go through here is basically the fundamentals of what is involved in this technique. So basically, in mass spectrometry, what we try to do is try to determine the mass to charge ratios of particles. And we use an instrument known as a mass spectrometer to do that. And the record of the separation of the ions in this particular experiment is called the mass spectrum. And an example of a mass spectrum here is shown to the left here. This is basically the mass spectrum of helium. And what you have here is a plot of the relative number of atoms versus the mass to charge ratio, all right? And you'll notice that the one here with the biggest peak is the ion, which has the mass to charge ratio of 202, all right? So this is the most abundant ion present in the mass spectrum. So we're going to see how we end up with this mass spectrum. And basically what we do is that we convert the atoms or molecules, in this case it's an atom or an element, mercury, we convert it to ions. And basically how this is done is that we, well, there are several ways, but firstly you have to convert it into a gaseous stream, and then in some cases they bombard it with electrons, or they probably heat it, and there are different techniques that are used to convert the atoms of mercury to iron. and then to ions, and then those ions are allowed to pass through this region. Now, this region here will have a magnetic field, right? And it turns out that the magnetic field will have an effect on how the electrons are deflected. We saw that earlier when we looked at the formation of cathode rays. Now, it turns out that the ions which are lighter in mass will be allowed to turn, or will be forced to turn in a more tighter circle as shown here. And then as the mass becomes greater, the radius of the circle of travel becomes greater. So it's more difficult to deflect the heavier ions. So that basically is the basis for the separation of these ions. The lighter ones will follow a tighter circle. The heavier ones will travel a distance which involves a larger circular path, right? And therefore, because of that separation, when they hit the photographic plate, which is shown here, right, you'll see that the intensity of the lines on the photographic plate will be reflective of the number of particles, relative number of particles responsible for each line. And it's on the basis of that, you can see here that in this case, the mercury ion, which has a mass of 202, has the brightest line. So therefore, of these ions that were formed coming from this region here, the mercury ion, which has the mass to charge ratio of 202, would be the most abundant of these ions present. All right, so that's basically what is involved in mass spectrometry. Okay, we're going to stop this video here at this point, and then the next topic would be wave motion.